on June 1st after 1 year using this equation over here. Okay, so question B is asking how long will it take for the insecticide concentration to decrease to 3.1 times 10 to negative 7 gram per centimeter cubed. Okay, so it is asking for time and it is providing the later concentration. So and since we know that we can use this equation, we already know rate constant, okay, and we already know the initial constant, okay, and then we already know the later concentration, which is provided in the question. Okay, so we're going to solve for T, the time it takes for the concentration to decrease to 3.1 times 10 to negative 7 gram per centimeter cubed. Okay, so just plug in everything that we have. Natural log of 3.0 times 10 to the negative 7 equals to negative. The rate is provided to be 1.45 year inverse year, and then times T plus natural log of initial concentration is provided to be 5 times 10 to the negative 7. Okay, so plug these values in your calculator. Natural log of this value gives negative 15.02 equals negative 1.45 inverse year T natural log of negative 14.51. Okay, if you solve for T equals to negative 15.02 plus 14.51 divided by negative 1.45. That gives you 0.35 year. So this is the time it takes for the concentration to become 3.0 times 10 negative 7 gram per centimeter cubed. Okay, let's solve another sample exercise.
Can I see that example one more time, please?
Oh, sure.
Sorry. Also, how did you get negative 15.02 plus where is it? I'm sorry, I can't see it. Plus 14.51. Like, did you subtract it from the other side or?
Okay. So if you move this to here, T will equal to This entire thing divided by this. Does that make sense?
Yes, thank you.
Okay. All right, let's read the question together. The following data were obtained for gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. Okay, so in this reaction, the nitrogen dioxide is decomposing into nitrogen monoxide and oxygen. Okay, so the question is asking whether this reaction is first order or second order. And as we observed previously, if it is first order, the plot is linear for natural log of concentration, initial concentration versus time. Okay. If the reaction is second order, the plot is linear for 1 over initial concentration versus reactant concentration versus time. Okay, so what we have to do is we have to, you are provided a molar information, and you want to convert this into natural log of NO2, and you want to convert this into 1 over NO2 concentration. And then you want to plot it and see if which one gives you linear line. So whatever gives you linear line, that will determine whether it's first order or second order. Okay, so with the given concentration, plug these values into calculator, and you find for natural log of concentration of NO2. Okay, these are the values that we found. Okay, and then if you plug in these concentration value into your calculator, so 1 divided by all of these concentrations, you get this value. So then you want to graph this. So it's going to be, this is going to be your y-axis, and this is going to be your x-axis. Okay, so if you look over here, the first graph, number 1, is a graph of natural log of NO2 versus time. Okay, so this versus this. Okay, for the second graph, this is 1 over NO2 concentration on y-axis, and x-axis is time. Okay, so as you can observe from here that the graph number 2 gives you a straight line. Okay, so because 1 over NO2 concentration versus time gave you linear line, this tells us that the reaction is second order. Okay, so let me actually quickly summarize whatever we learned from Tuesday, because it seems like we covered a lot, and it might be confusing for a lot of you guys. So the first thing that we have learned is zero order reaction. Okay, the equation is concentration at some time t equals negative kT plus initial concentration. Okay, so zero order reaction basically tells us that the rate is independent of the concentration of the reactant. Okay, and then we learned first order reaction. Okay, first order reaction has an equation of natural log of concentration A at some time t, negative kT plus natural log of initial concentration. Okay, first order reaction basically tells us that some reaction rates depend only on one reactant to the first power. The third concept we learned is the second order reaction. Okay, this second order reaction has equation of 1 over concentration at some time t equals to 1 over initial concentration plus kT. Okay, second order reaction basically tells us that sometimes rate of the reaction depend only on a reactant to the second power. Okay. So here, second power, and here, sum of the power will be 2. Okay. The fourth concept that we covered was half-life of first order reaction. Okay. This had an equation of T 1 over half-life time equals to 0.693 over K. Okay, so half-life basically means the amount of time required for a concentration to become half of the initial concentration. Okay, so for half-life reactions, the later concentration, these AT, these are the later concentration. Later concentration is already set. The later concentration after some time t will be half of the initial concentration. Okay, so for a first order reaction, the time it takes for the concentration of the reactant to reach half of its initial concentration, as you can see, it's independent of the initial concentration. There's no initial concentration involved in this equation. The time it takes for the concentration of the reactant to reach half of its initial value is 0.693 divided by rate constant K. That's it. The fifth concept that we learned was half-life of second order reaction. Okay. This had an equation of time requires to reach half of the initial concentration equals to 1 over K initial concentration. As you can see here, there is initial concentration involved in the equation. So for a half-life of second order reaction, the initial concentration matters. Okay, so for a second order reaction, the time it takes for concentration of the reactant to reach half of its initial concentration value is dependent on the initial concentration. Okay, and so these are the 5 concepts that we covered on Tuesday. Okay, I hope this summary helps. So let's do a practice example exercise for half-life of a first order reaction. So this is a reaction of C4H9Cl with water. Okay, and they already told us that this is first order reaction. Okay, so use figure 14.3 to estimate, this is figure 14.3, to estimate the half-life for this reaction. Okay, and then question B is asking us to use the half-life from A to calculate the rate constant. So from the graph, we see that the initial value is 0.1 mole. Okay, so this reaction started off with 0.1 mole. Okay, so it's asking to estimate the half-life for this reaction, means it's asking for time for this concentration to become half of this value. So 0.1 divided by 2 is going to be 0.050. The question is asking for a time for this concentration to become this concentration. So how long does it take for 0.1 mole to become 0.050 mole? That's basically what question A is asking for. So you can go to this graph and find a point where 0.050 drops. So 0.050 is around here, okay? And then if you go to the x-axis, the time for the initial concentration 0.1 molar to become half of its concentration 0.050 mole is going to be about 340 seconds. So after 340 seconds, this concentration will become half, 0.050 mole. Okay. For B, okay, we need to find the rate constant. Then we need to bring the half-life equation. So half-life equation is this. Okay. So then we can solve for K because we already know the half-life time. Okay, so the rate constant K is going to be basically 0.693 divided by half-life time. Okay, so 0.693 divided by 340 seconds is going to be 2.0 10 to the negative 3 inverse second. So as you can see over here, we don't really need much information to find out rate constant K for the half-life reaction and to find the time it takes, the half-life time for first order half-life of a first order reaction. Okay. And we've been dealing with reaction rate, and there are various factors that affect the reaction rate. And we're going to study in detail how and why these factors affect the reaction rate in the following sections. So these are the 4 factors that affect the reaction rate. Number 1, temperature. Number 2, frequency of collisions. Number 3, orientation of molecules. Number 4, energy needed for the reaction to take place. So the rates for most chemical reactions increases as temperature increases. So increases as temperature increases. So rate constant K that we have encountered in previous equations is temperature dependent, where rate constant increases as temperature rises. Okay, so because rate constant, so when T increases, rate constant increases, and reaction rate, and this tells us that reaction rate is increased. Every 10 degrees Celsius of temperature rise, the rate constant will double. Okay, so here the diagram, the picture on the right side, the example is showing the chem-illuminescence reaction in light sticks in hot water versus cold water. And as you can see, the luminescence reaction is more vigorous in the hot water, which is producing stronger light compared to the cold water. So more vigorous, faster, stronger reaction in elevated temperature versus lower temperature. So the collision model, I've already covered this in the beginning of beginning of this chapter, but the collision model explains that when you have greater number of collisions, you will have greater reaction rate. So what will cause greater number of collisions? Okay, so there are two things that can create the increase the number of collisions. Number one is increasing T. And then number two is increasing reactant concentration. Okay. So for increasing temperature, according to the kinetic molecular theory of gases, increasing the temperature increases the molecular speed. Okay, this will increase Therefore, if the molecule is moving way faster, it will collide more frequently. Okay, then because of higher frequency of collision, there is more reaction. For increasing reactant concentration, if you have more reactant in a certain volume, definitely when you have higher concentration of reactants, this will allow more collisions to occur, more chances for these molecules to bump into each other, and therefore causes faster reaction. Okay, so that's what the collision model is. Orientation of molecule is also very, very important, determining affecting the reaction rate, because not all collisions allow successful reactions. Okay, molecules can often collide without forming any products. Okay, molecules need to have proper orientations for proper reactions to occur, and when atoms are properly positioned to form new bonds, then this formation of new bonds allow chemical reactions to take place. So if you look at the example over here, this is a formation of, this is chlorine, this is chlorine. Okay, if you have two molecules, if you have chlorine properly aligned with chlorine of this NOCl, then only then there will be proper collision, and this collision allows new bond to form. However, if this chlorine, although there is collision, if it bumps into nitrogen side of this NOCl, then this collision will not create new bond. Okay? So only when atoms are suitably positioned to form new bonds, this formation of new bonds will allow chemical reactions to take place and form the right product. Okay? So the final factor that will affect the reaction rate is energy needed for reaction, the activation energy, energy needed for the reaction to take place. And next 7 slides, we'll be focusing on this activation energy. Okay, so all molecules possess a certain minimum amount of energy to react or to initiate a reaction, and this is called activation energy. Okay, and the diagram here is showing a golfer hitting the ball to make the ball move over the hill, okay, in the direction to the cup. The hill is a barrier. This hill is a barrier between ball and the cup. Okay. Enough kinetic energy is needed for the ball to pass the hill and get inside the cup. If the golfer does not provide, or if he doesn't impart enough kinetic energy, the ball cannot pass the hill and the ball will just roll back to him. Okay. So again, the minimum energy is energy the minimum energy needed for a reaction is an energy barrier. This is an energy barrier, and this minimum energy is called activation energy. Okay. So just as we seen from the previous diagram, when the golf ball is at the top of the hill, it's considered to have highest energy state, or the highest energy to roll down the hill. So in a chemical reaction, when a reaction has enough activation energy, the molecule will also reach the molecule is also going to reach the top of the hill before it rolls down the hill. And when the molecule is at its highest energy state, this is called transition state. We can say the molecule is at transition state. So let's take a look at some specific examples on the next slide. So this is the energy profile of methyl isonitrile converting into acetonitrile. And this is a first order reaction where a single reactance is required to generate the product. Okay. This is the diagram shows that energy must be the diagram shows that the energy must be supplied to stretch the bond between this CH3 methyl group and this methyl group and this cyanide group. So this bond right over here, this bond that's connecting, which is connecting carbon and nitrogen, that needs to be, you need to have enough energy for that bond to be stretched out. Okay, once this bond is stretched out, once it has enough energy, this bond will stretch, and once it has, and it will twist to have such an orientation like this. Okay, so once it has enough energy for the bond to get stretched, it will twist, it will rotate, and it will have this form of state. Okay, and then through this orientation, slowly the CC bond is going to be formed. Okay, and the energy of the molecule drops down. The barrier to form the final product represents the energy necessary to force the molecule through a relatively unstable intermediate. Unstable intermediate state, or you can say twisted or rotated state. So this unstable intermediate state is called transition state. Or you can also call it activated complex. Okay. So this transition state right here is analogous to the ball at the top of the hill from the previous slide. So again, to summarize what I've explained so far, the diagram is clearly showing that the molecule must have enough energy to rotate the cyanide group in order for the new reaction to take place. If the molecule does not have enough activation energy to form this activated complex or the transition state, there will be no reaction. Okay. So the y-axis of the energy profile is normally potential energy. Okay, and then the x-axis is the progression of the reaction. And as you can see from the diagram, the product is at lower energy state than the reactant. Okay, so because the product is at lower energy state than the reactant, the energy change for this reaction is, which is a delta energy. reactant is going to be negative value, okay? And therefore, this reaction is considered exothermic, okay? So how about a reverse reaction? How about when you're performing a reaction where acetonitrile is becoming methyl isonitrile? So as acetonitrile, then if you're going from acetonitrile to methyl isonitrile, what's going to happen is that the reactant energy is going to be the product energy state is going to be higher than the reactant energy state. In this case, the delta energy is going to be positive, and then this reaction is going to be considered endothermic. Okay. So let's review some of the vocabularies that we learned so far. Activation energy is the minimum energy needed for a reaction to take place, and it's called you can also use this notation, EA. Okay, this is a minimum, or you can also explain that it's a minimum energy to overcome the energy barrier of the reaction. Okay, transition state or activated complex is an unstable intermediate at highest energy state or intermediate found at the top of the energy barrier. Okay, again, it's an unstable intermediate at highest energy state. As you can see, it's at highest energy state. And this is an intermediate found at the top of the energy barrier. This is your energy barrier. The hill is the barrier. Okay. And we also learned about exothermic reaction and endothermic reaction. When product is at lower energy state than reactant, when product is at lower energy state than reactant, the reaction is exothermic. The reactant released energy during the formation of the product. Okay, and for endothermic reaction, when the product is at higher energy state than the reactant, the reaction is considered endothermic. Okay, so that's some of the quick summary of what we have learned so far. All right, so as we learned previously, increasing temperature will increase the reaction rate. Okay. At higher temperature, much greater fraction of the molecule, not all molecule, but much greater fraction of molecule, okay, have kinetic energy greater than the activation energy, and which eventually leads to a greater rate of reaction. So in summary, increase in temperature allows molecule to have more energy to overcome the energy barrier of the reaction, and this leads to the increased reaction rate. Okay. So this is the explanation regarding why increasing temperature increases the reaction rate. Increase the reaction temperature will allow more energy. The temperature will provide more energy for the molecule to overcome the energy barrier of the reaction, and then that's why, in result, increasing reaction rate is observed. Okay. And here is an equation describing the relationship between activation energy and temperature. This is a relationship between activation energy and temperature. Okay. Arrhenius came up with this equation, so it's called the Arrhenius equation. Okay. And he came up with this equation through various reaction rate data that he has collected. Okay, so this is from the actual data that he collected. And the Arrhenius equation is, so if you look at the equation, the Arrhenius equation is rate constant K equals to this, a capital letter A is a frequency factor. Frequency factor means the frequency of appropriate collisions. Remember, we observed in previous slides that we need the appropriate collisions to occur for the reactions to take place. So this is that frequency factor. Okay, and then it's frequency factor times e to the power of negative activation energy divided by RT. R is a gas constant, 8.314 joule per mole Kelvin, and then T is going to be the absolute temperature. One thing to keep in mind is that this temperature has to be in SI unit. So it's going to be in Kelvin. Okay. So this mathematical expression basically tells us that the rate constant K will increase as the activation energy increases. Okay, and or you can also say that if you lower the activation energy, the rate constant K will become larger, and then this allows faster reaction. Okay, so lower the activation energy, larger the, oops. If you lower the activation energy, the larger the rate constant and therefore faster reaction. That's what this mathematical expression is explaining. Okay. Let's do a quick sample exercise. So consider a series of reactions having these energies profiles. Okay, so this is the energy profile for experiment 1, 2, and 3. You need to rank the rate constant from smallest to largest. Okay, assuming these reactions have nearly the same value of frequency factor, the collision, appropriate collision factor A. Okay, so the question is asking us to rank from smaller k to larger k. So what will have smaller k? From the previous equation that we observed here, we know that in order for the to have smaller rate constant, you need higher activation energy, or higher activation energy will cause smaller rate constant k, right? So from these three diagrams, we need to find the one that has highest activation energy. Okay, so the activation energy portion is going to be from the reactant's potential energy to the top of the energy barrier. So this portion is going to be the activation energy. Okay. The final products energy state is not important in this question. Okay, so if you compare three activation energy, we see that reaction number 2 has highest activation energy of 25 kilojoule per mole. So this reaction will have smallest rate constant K, okay, because it has highest energy barrier. Okay, so reaction number 2 will have smallest K, and then followed by reaction experiment number 3. Okay, it has activation energy of 20 kilojoule per mole. That means because you have higher activation energy, that you are going to have because 20 kilojoule per mole is a slightly smaller activation energy compared to 25. It's going to have slightly larger K compared to experiment 2. Okay? And then the experiment with smallest activation energy, 15 kilojoule per mole, will have highest K. That means the reaction constant, reaction rate is going to be highest for experiment 1. Okay, so we can calculate the activation energy by manipulating the Arrhenius equation. This is the Arrhenius equation, and we can calculate the activation energy by manipulating this equation. By taking the natural log of both sides of Arrhenius equation, we get this expression. Natural log of K equals to negative activation energy over RT plus natural log of the frequency factor. Okay, and if we have to deal with a reaction that is affected by 2 or more temperature, T1 and T2, we can use this below equation. So we derive this equation by subtracting natural log of K2 from natural log of K1. So natural log of K1 minus natural log of K2 will allow this expression. Okay, so you can use either this or this. When you have 2 or more temperature involved, you will want to use this equation. Okay, so this equation has a form of equation for a straight line. Y equals mx plus b. So y mx.
Can you go back to the slide real fast?
Oh yeah.
Thank you.
Mm-hmm. Okay, so this portion is y, this portion is mx, and this portion is b. Okay, so if you plot this graph of natural log of k versus, let me rearrange this equation.
That negative sign will always be there no matter what, right?
What's that again?
That's the negative. That's always
Yeah.
going to be there no matter what, right?
Yes.
Okay.
This is the set equation. Okay, so this portion is y, this portion is m, this portion is x, this portion is b. So if you were to plot a graph of natural log of k versus 1 over t, natural log of k versus 1 over t, this is going to give you a straight line, and the slope is going to be negative activation energy over r. Okay. Let's solve one practice example. Okay. So the table at right, this table here, shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. So the first order reaction that we observed previously. Question A is asking, from this data, calculate the activation energy for this reaction. Question B is asking, what is the value of rate constant at 430 Kelvin? Okay, so the approach should be that we know this equation. Okay, we know this equation. We derive this equation from Arrhenius equation, and we know that the negative activation energy over R is going to give us will allow us to calculate the activation energy they're asking. However, we don't know this portion yet. Excuse me. But we can find this by finding the slope of this data. Okay, so using the data that provided, we're going to graph this. Okay, so in order to graph, as I mentioned in the we need to graph natural log of k versus 1 over t. Okay, but what we have here is temperature and k. Okay, so we need to convert this into 1 over t and natural log of k. Okay. Again, the temperature needs to have a unit in Kelvin, the SI unit. So we need to convert this degree Celsius into Kelvin. Okay. So when we do all those conversions, we arrive at this table. So all the temperature in Celsius is converted to Kelvin. Okay, and they're over here. And then all the rate constant is now changed to natural log of rate constant. Okay, this temperature that has been converted to Kelvin, if you do 1 divided by these values, you get this data. And if you plot this versus this, you will get this. Okay, so since you can't use a graphing, so if you plug these values in a graphing calculator, or y versus x versus y, easily you can graph this. Okay, but since you can't use graphing calculator during an exam, if you have to graph, a much simpler value will be provided for you, and you should be able to hand graph and figure out whether it forms a straight line or not. Okay, so yeah, these values I plug it into the graphing calculator, and then we got this. So from this we can see that the graph gave us straight line, and we immediately know that the slope is going to be negative activation energy over R. Okay, so this is a slope, a straight line. And when you can use any 2 points to find out the actual slope. Okay, so let's say we pick a random point. Let's say we picked negative 6.6. Okay, that will have x value of about 0.00195. Let's say we need to pick a second point if you want to find a slope. So let's say we pick this. Negative 10.4. The x-axis is going to be about 0.00215. So in order to find the slope, the equation of slope is going to be delta y over delta x, right? The change of change of y-axis over change of x. So then if we plug these values in here, we can do y1 minus y2 over x1 minus x2 will give you the actual value of numerical value of slope. Okay, so we just have to plug in all these numbers. We have negative 6.6, negative 6.6 minus negative 10.4 divided by 0.00195. This is inverse temperature, so it has unit of inverse Kelvin, minus 0.00215, again inverse Kelvin. Okay? So if you do the math, plug these values into calculator, you will get negative 1.9 times 10 to the 4 Kelvin. Okay? So now we know the slope. And we know that slope is equal to negative activation energy over R. Can you find activation energy?
So we can use this method always to figure out the slope.
Are you talking about this over here?
Yeah, the way you used
Yeah.
1 over T and L and K,
1 over
natural
T.
log of K.
Oh, okay, what is your question?
So can we always do that? So we can just take the natural log of K and the 1 over T to figure out how to graph it, and then we can use that graph to figure out our slope.
When you say always, it's kind of tricky, but you should always use this for when you determine activation energy. So different question will, remember when you were dealing with first order reaction, you have different y-axis and different x-axis. So this particular problem, we're solving for the activation energy. So when your equation has this form, yeah, of course you can use natural log of K for y-axis and 1 over T for x-axis. But if you have different equation, you can't always use this. Does that make sense?
Yeah, it does.
Yeah.
So it would only work for activation energy.
Of course, yeah. It will only work for this equation specifically.
Right. Okay, I get it now.
Yeah.
Thank you.
Okay, so for let's solve for activation energy. It's going to be negative of the slope multiply R. Okay, so then negative of negative 1.9 times 10 to the 4 Kelvin multiplied by the gas constant is will always be provided, or if you have to memorize, I will put it into the list that you need to memorize before the exam. Okay, so 8.314 joule per mole Kelvin. Okay, so the Kelvin is going to cancel, and you're going to be left with negative. If you do the math, plug these values into the calculator, you get negative 15.7966 times 10 to the 4. And you're going to be left with joule per mole. Okay, so because you only have two significant figures here, you want to reduce this into two significant figures as well. So you will have 1.6 times 10 to the 5 joule per mole. This is going to be your answer. So SI unit for energy is joule, so joule per mole is perfect enough. But let's say if the question asks you to convert this into, provide answer in kilojoule, can you convert? Okay, so I will show you a quick conversion, but this question specifically, they did not ask us to convert and provide answers in kilojoule, but I'm just showing you just in case the exam asks you for the conversion, okay? So because 1 joule is equal to 10 to the negative 3 kilojoule, anything that has kilo is going to be 10 to the negative 3 fractions of something, right? So if you have or a thousandth of a joule, okay? So then 1.6 times 10 to the 5 joule per mole is going to become 1.6 times, if you do 5 minus 3, then you have 10 to the 2 kilojoule per mole. Okay? Or this is simply 160 kilojoule per mole. Another thing to pay attention is that when you provide answers in scientific notation, this value in front of 10 to the something always has to lie between 1 and 10. Okay, so if you provide answer in scientific notation such as 16 times 10 to the 4th, this is going to be incorrect. Okay, because this has to be a number between 1 and 10. Okay, so we finished question A. Activation energy is calculated to be 1.6 times 10 to the 5 joule per mole. Okay, so question B is asking to find the rate constant at 430 Kelvin. Okay, so the temperature is provided. Okay, and we need to find rate constant K. And because various temperature is used, here, as you can see, various different temperature is used, we will use this equation. So this reaction is convenient because it allows us to calculate rate constant K1 at T1 when we already know rate constant of K2 and T2. Okay, so when we already know these two values, we can simply use this equation to find out these. Okay, so this is a convenient equation. Okay, so if you were to use this equation in the beginning, you will need this frequency constant. But if you have this equation, you don't even need the A value. Okay, so and we already have a lot of experiments provided where we know various different constant K and various different T1 value, various constant K and various temperatures. We will plug in these to find out the rate constant K1. Okay, so what we're going to do is we're going to pick random K2. Okay, so we're going to pick random K2 and pick random T2. So I'm going to just pick this rate, okay, and then this temperature. This temperature is Celsius, we can't use, so we're going to use this temperature. So K, and please don't get confused between this K versus Kelvin K. Okay, this is smaller K and this is capital letter K. Okay, so the rate constant K2 is that I picked from this table is going to 2.52 times 10 to the negative 5. Unit is inverse second. The T2 is going to be for that specific reaction, 189.7 degrees Celsius convert to Kelvin is going to be 462.9 Kelvin. Okay, we're going to plug all of this information, and we already have T1 provided from the question. We're going to plug all of these into this equation to find for K1. Okay, so natural log of K1 divided by K2 is this value, 2.52 times 10 to the negative 5 inverse second equals to the activation energy is what we calculated in question A. It had a value of 1.6 times 10 to the 5th joule per mole, okay, divided by gas constant, 8.314 joule per mole Kelvin, okay, and then we know T2. T2 is 462.9 Kelvin, 462.9 Kelvin minus, you know T1 is 430 Kelvin, 430 Kelvin. So if you do the math, natural log of, plug these values in the calculator, equals to, here, let's do some unit cancellation. Joule per mole will cancel, okay, and you're going to be left with inverse Kelvin, okay? So let's do this portion of the math. You get 0.19 times 10 to the 5th inverse Kelvin. If you do this portion of the math, you have negative 1.65 times 10 to the negative 4 Kelvin. Okay, so this will equal to negative 0.318 times 10. Which is negative 3.18. Okay, and oh, another unit cancellation. Inverse Kelvin and Kelvin will cancel each other. You're going to be left with a number without a unit. Okay, so K1 over 2.52 and to the negative 5 inverse second is going to be equal to e to the negative 3.18. Okay, and this value, you plug this into the calculator, you get 4.15 times 10 to the negative 2. Then we can easily find K1, which is 4.15 times 10 to the negative 2 divided by 2.52 times 10 to the negative 5 inverse second equals to 1.0 times 10 to the negative 6 inverse second. This is going to be your final answer. Okay, so again, when you know K2, you know T2, and when you already know T1, you can use this equation to find a known K1, okay? Or if you know all these three values and you're required to find this temperature, you can also use this equation to find this T1 as well. Somebody had a question?
No, I'm just gonna ask if you could just pause really fast while I write this down.
What's that again?
Can you just give me a second for me to write this down before you go to the next slide?
Oh, yeah. Okay, so this is end of today's lecture. I'm going to hang around for another 5-10 minutes just in case anybody else has questions. Since I can't read the chat, the chatting area, If you have any question, please unmute your microphone and just feel free to speak up.
Dr. Lee,
Yeah.
can you just, I know it's just, can you just go, okay, so you know the last line starting with K1?
Mm-hmm.
Can you go up that one last line? How did you get there?
Here, natural log. of
Okay, so
X.
I know how you got there from the natural log, and then you just did simple arithmetic. Then I got kind of lost when you got rid of the natural log.
Oh yeah, okay. So just the algebra again. If you have natural log of x equals y, this equals to x equals to e to the y. This is the algebraic rule.
That's right.
I didn't come up with this.
No, I remember that.
Yeah,
That's
yeah,
right. I'm sorry about that.
yeah. Take a note of this. You need to be familiar with this.
No, yeah, I
Yeah.
just, thank you.
Mm-hmm.
So when we solved for the negative 3.18, we were
Mhm.
basically solving for y, right?
Solving for y. Correct. Yeah.
Okay, thanks.
So basically, this portion is x. This entire portion is y. Yeah, I know it's a big math, but this is what you have to do for your exam. Okay, so Gen Chem 2 math is pretty challenging because it involves a lot of challenging units, and you really have to pay attention to the units throughout the math. You need to do a proper cancellation, proper multiplication, proper dimensional analysis, remember, from Gen Chem 1. Yeah, so there are a lot of things to pay attention to, but yeah, but practice will get you comfortable.
Dr. Lee,
Yes.
I have the same question as from the chat. Why do we need to divide instead of multiply from, K1 equals 4.15 divided by the 2.52?
Oh, I'm sorry, what's your question again?
Why do we divide instead of multiply it?
Why do you divide instead of multiply? So here, K1, here, are you talking about this portion? Why you divide?
Yes. Yes.
Okay, so K1, let's say you have X, and let's say you have Y. K1 will be Y over X. Oh, oh. Oh, that's right. Oh, my mistake. Did I make a mistake? Oh my gosh, I made a mistake. I made a mistake. This is totally wrong. Yeah, good point. Thank you for pointing that out. It should be multiplication. Yeah. So 4.15 times 10 to the negative 2 times 2.52 times 10 to the negative 5. Yep. Okay, whoever pointed that out, thank you. I made a mistake. Let me actually write that more neatly. K1 equals 1.15 10 to the negative. Okay.
Thank you, Dr. Lee. Have a good weekend.
Okay, bye.
Dr. Lee,
Yes.
I have one last question. How did you get, well, where did you get 4.15 from?
4.15?
Yeah, times 10 to the negative 2.
Here. You use your calculator, you put e to the power of negative 3.18, you'll get 4.15 times 10 to the negative 2.
Oh, okay.
Yeah.
Thank you.
Mm-hmm.